All right, we've got one last section for chapter 11, and this is radical polymerization. This is a really big field in organic chemistry, that is polymer chemistry. And radical polymerization is one of the two main types of polymerization. There's radical polymerization, and does anybody know the other type? Non-radical or condensation polymerization. Condensation polymerization we'll cover later, but that's where you kick off some sort of small molecule like water as a byproduct. Radical polymerization is actually very efficient. It doesn't produce any byproducts or waste. So I'll show you guys how this works. With radical polymerization, you start out usually with some sort of monomer that has an alkene in it. Monomer meaning one mer. Nobody laughed at that. And then what you're going to do is polymerize it. And what you're going to do is change this alkene into a big, long, repeating alkane. And what we do to show this, let me even accentuate this even more, is we put brackets around it. And then we'd say, all right, the carbon on the left-hand side had two R groups coming off. Same with that one. And then what you can do is put some sort of number or number range down in the bottom to indicate how many repeat units of this that you have. So some polymers can be quite short, so maybe 5 or 10. Other ones can be up into the hundreds of thousands or millions. Theoretically, this could go on forever. It really just depends on how much of your monomer you have around, right? All right, so let's take a look at this and how it relates to a lot of the common polymers we see in our day-to-day life. All right, the first one that we have is ethylene. And when we polymerize it, same thing, I'm going to put one big bracket in here and put two carbons. Oop. Each of these carbons has hydrogens coming off of it. And I'll put some sort of number on the outside. What do you think this polymer is called? Yep, polyethylene. Pretty fancy. Does anybody know what polyethylene is used in? Does anybody have a plastic water bottle? I think I see an Aquafina bottle back there. You guys see that? Those are made of polyethylene. There's high-density polyethylene and low-density polyethylene. They're really common. The high-density ones are the ones that don't have much branching, which means these big, long ribbons stack really tightly and they're more rigid. The low-density polyethylene is similar to what you might see on a bike water bottle. They're the squishier types. They almost feel waxy. And it's commonly used in all sorts of consumer plastics. This is arguably the most produced plastic on the planet. I believe it is still. All right, so that's one main type. Let's take a look at the next one. This is called propylene. This does confuse students. They say, well, why is it called propylene? Shouldn't it be called, what, 1-propene? It just doesn't sound as fluid to say 1-propene, so people rename this propylene. Same thing with ethylene. People call it ethylene just because it sounds easier than ethene. Ethene oftentimes just doesn't sound right to chemists, so they go with these old school names. So same thing with the polymer. We can go ahead and fill out our bracket and say, all right, we're going to have some repeating units of carbon in here that repeats some number of times. The carbon on the right-hand side this time has two hydrogens attached. The carbon on the right this time has a hydrogen and a methyl group. All right, so what do you think this polymer is called? Polypropylene. Does anybody know what polypropylene is used in?
A lot of surgical wrap stuff is polypropylene.
Yeah, it's used in a lot of surgical equipment. Some carpets are made of it. Oftentimes camping gear is made out of it. Do you guys know why polypropylene is more popular than cotton? Doesn't burn? It can burn, actually. Don't test that one out. Does anybody know the other reason? Any hikers? It's not waterproof. Lightweight. At least the clothing type. It's lightweight. When cotton gets wet, it stays cold, right? If you're wearing a t-shirt and you get wet, you're going to be freezing. If you wear polypropylene and you get wet, you can still retain a lot of that heat. And so it's really common in clothing and carpeting and things like that. It's also very durable. All right, the next one we have that's really popular is this one, and this is called styrene. And same thing with styrene, we can polymerize it. So I'm just going to do a big long repeat unit. So the left carbon has 2 hydrogens, the right one has a phenyl group. I'm just going to abbreviate it. It's important to remember that you can always abbreviate these rings as a pH, right? And of course, this would be called polystyrene. And I heard somebody say what this is commonly known as styrofoam, right? So if you've ever worked with packing peanuts or styrofoam, this is usually polystyrene. There are some alternatives out there right now. If you ever order stuff, Amazon doesn't really do it. I'm trying to remember which company does, but they actually have biodegradable ones now that are made of biopolymers. Those are getting more popular because this is really tough to recycle. People typically don't recycle polystyrene because it's so lightweight and it takes such an incredible amount for it to be economically viable. It's just not worth the transportation costs. So they are trying to phase this out, but it is still a big commercial plastic. All right, let's do a couple others. Next one we have has a chlorine off of it. So now we've got 2 hydrogens over here. I'm going to actually move this up a bit. A chlorine and a hydrogen. The monomer in this case is called vinyl chloride. Vinyl is another word for an alkene, essentially. And that means that the polymer in this case is called polyvinyl chloride. Does anybody know what this is most commonly called? PVC. So most of your houses, if you look at the pipes, those pipes are going to be made of PVC. PVC is incredibly long-lasting. It doesn't break down very easily, which is why it's used in things like piping. You don't want your pipes to degrade after 20 years. You want them ideally to last 40-plus years. And this is an incredibly durable plastic, too. All right. I think I've got one more, and this is one of my favorite ones. So we've got this tetrafluoroethylene alkene. When we go ahead and we draw the polymer that's to be expected, it'll look like this, where it looks like polyethylene, but all of the hydrogens are now swapped out for fluorines. Oops, let me move this over. And this is called tetrafluoroethylene. And that means that the polymer is polytetrafluoroethylene. Oftentimes, this is just too long to name, so people call this PTFE. Does anybody know the commercial name for this, the brand? Teflon, exactly. Does anybody know what Teflon's used in?
Cookware.
Cookware, right? Why do you think it's used in cookware? It's non-stick, exactly. If you look at this too, it's very hydrophobic. It does not have anything that wants to bond to water in there. And because of that, it's great for cooking. However, a lot of people are a little bit suspicious about this for a few reasons. One is the industrial process used for making Teflon is pretty harmful for the workers in those plants. And so there are a lot of news stories out there about workers in those plants having an obscenely high rate of cancer or health problems. The other one is when you cook with Teflon, you have to be very, very careful with the heat. If your heat gets too high, you'll actually start chipping off that Teflon, and then if you ingest it, that's probably not the best thing in the world. And then it's gonna end up going through you into the environment. Carbon-fluorine bonds are incredibly rugged. They will rarely break down, which means this will persist in the environment. Another offshoot problem of this is if you're into skiing at all, a lot of the really popular high-end ski waxes are actually pretty similar to this because they're hydrophobic. So they use these fluorinated waxes. What they're finding is that fluorinated stuff is ending up in our ecosystem and bioaccumulating. So a lot of people are a little bit suspicious of this, saying if we are going to make plastics, maybe fluorinated plastics aren't the best. And so you are seeing a big push where people, instead of getting Teflon, are actually going back to 1800 style cookware and using cast iron. So it is something to think about the next time you're looking at buying pots and pans, is whether or not you do want something with Teflon in there. Some people just use stainless steel as well. Does that make sense? I just wanted to show you guys a handful of these. There are a lot of other radical polymer products out there. These are just the biggest commercial ones.
For polyethylene, at work we have polyethylene glycol. What's the...
Yeah, so that's a good question. I didn't mean to cover this. So this is a little bit different. Polyethylene glycol is something that looks like this, where you have a repeating number of units in there. And this unit right here and right here, you see how it's 2 carbons long? These are called ethylene spacers. And a glycol refers to a diol, meaning you've got an alcohol coming off of each end. So this would be polyethylene glycol. This is really common in the biomedical field because it'll dissolve both organic compounds and aqueous compounds. So it's an amphiphile, almost like soap. And so it is commonly seen in things like pharmacies. Great question. All right, so let's go and look at the mechanism for this. The mechanism for this looks a lot like all of the other radical reactions we've seen. What's the first step always going to be? Initiation. And I will be honest with you, most plastics have very, very specific initiators. These have been studied very extensively by companies like DuPont. However, our textbook just goes with the peroxide route because it's easy. It says, all right, for this one, we're going to cleave the peroxide into 2 radicals. So now we've got 2 free radicals floating around. And I'm just going to do polyethylene for this one because it's got the easiest substituents. And in the next step, we're going to add this to our pi bond. So this is going to steal 1 electron from the pi bond, form a new covalent bond, and then the leftover electron will get dumped to that terminal carbon. And I'm going to show the hydrogens for right now, just so we can keep track of everything. Whoops. And then later on, I won't show the hydrogens just to make it simple. So we've initiated our radical. Now what we need to do is propagate it, right? That's step 2. And with propagation, you're going to take this initial radical that we formed and we're going to try to lengthen it. So I'm just going to spin this around horizontally. And it's assumed that we've got a bunch of ethylene around as our monomer. And so it'll steal one electron from ethylene's pi bond, and then the second one will get kicked over, just like we saw before. And now we've added 2 carbons onto it, right? But it's still a radical. Yep.
I remember the second definition that the definition of initiation is where you have like a molecule that breaks into 2 radicals, but you got 1 radical and a molecule already in there. Why would that be?
So initiation, that's a good question. Initiation is any step in which you're creating a radical from a non-radical. So in our very first step, we started with peroxide, which is a non-radical, and ethylene, which is a non-radical, and we ended up with 2 radicals. So that's really the overall definition.
So that's what's happening on the first step?
Yep, in the first step, we have a non-radical, the peroxide. We're homolytically cleaving it into 2 oxygen radicals, right? And then with ethylene, that's a non-radical. We're reacting it with our oxygen radical, and now we're ending up with 2 radicals. So we're going from 2 non-radicals and ultimately ending up with 2 radicals.
But that on the bottom step, it's just 1 molecule and then just one of the radicals already, right?
Well, we've got a radical electron there and a radical electron there. We didn't have one here or here. Yeah.
Oh.
Sorry, they might be kind of hard to see, so maybe I'll bold them a bit more. There we go. All right, so we've got this propagation step. We can keep on doing this. We can say, all right, we've got this. This can react with the second equivalent of ethylene. Add 2 more carbons. And this can go on until your hand gets tired, so I'll let you decide when that is. But theoretically, if you've got an endless supply of ethylene, then you can make this an infinitely long polymer, right? All right, and then last but not least, we have to deal with the termination step. And termination, our goal is to go from 2 radicals to a non-radical. And just like we saw before, there's a couple different ways of doing this. And I'm going to even shorthand this. So I'm just going to write some number there. Sometimes people will write an N, other time they'll have a specific number. Sometimes you see the pound or hashtag symbol, it doesn't really matter. So that could be 1 branch, and this could react with a second one. And we could couple these 2 radicals together in a termination step. Let me zoom out a bit. Oh, I think I have too many carbons there. Actually, no, I'm good. Am I? Sorry. There we go. So you can do it that way, where you link 2 of your radical chains together. That's commonly seen. Or another common one that you might see is you still have that peroxide radical floating around. So maybe your peroxide radical could just couple with one of these chains, and you could end your end your propagation there. Sometimes what you might even see are specific polymers where they purposely put on an end cap and functionalize them in some way, but that's getting into more advanced chemistry and isn't as common with commercial plastics. But you can decorate them with end caps to serve a specific function. Does that make sense? All right, there is one last thing we need to consider too, and that kind of goes back to my discussion on polyethylene, where polyethylene I said could be high density or low density. High density obviously is packing more tightly, which gives it more rigidity, and that's used in plastics that are found in bottles. where low density is kind of that waxier, softer plastic, and it doesn't pack as tightly. And this has to do with something called side branching. And side branching is really common in polymer chemistry because radicals are super duper reactive. And this is due to the propagation step. So during propagation, you can have branching. We're not going to get into how this is controlled, but quite often you can choose an initiator or specific reaction conditions that will limit or promote branching of your main polymer. And they use this to control the overall macroscopic properties of your plastic. So let's take a look at what occurs during this step. So let's say you've got one of these propagation radicals, and then you've got another one floating around, and I'm just going to draw a central one here. In fact, let me zoom this out a bit. So this is the inside of a polymer chain, right? I'm not going to even bother showing the end cap. But what can happen here is this radical can actually abstract a hydrogen. And when you do this, you end up creating a radical in the middle of your chain. So that starting material we had is now terminated. It can no longer extend any further. But the other one that we had is now a radical itself. So these would be our two products from that step after the abstraction. And then this one can now propagate with ethylene. And when it does that, you still have a radical, but now it's coming off that ethylene side. And this can keep on reacting with more and more ethylene. And now we've got a big, long internal branch. The other thing that can also happen is instead of branching, you can have something called cross-linking, right? Because you can abstract hydrogens off two separate chains, and then they can actually link up together. And that's called cross-linking, and that also can be used to change the properties. We're not going to get into that too much, but I did want to show you a little bit about why this occurs. And it simply has to do with the fact that this first radical is so reactive, it'll react with ethylene or do a hydrogen abstraction depending on the reaction conditions. The key takeaway from this is side branching or cross-linking can affect the physical properties of plastics. Does that make sense? All right. Believe it or not, we're done with the chapter already. This was an unusually short chapter. So let's take a look at the reactions that we've seen. We actually only saw 3 different reactions. And so our fill-in-the-blank study guide will be a lot easier this time. Oh. All right. The first reaction we saw was the bromination of alkanes, and what reagents did we need to accomplish that transformation? Yep, Br2 and UV light. All right, what about anti-Markovnikov addition of bromine to an alkene?
HBr and peroxide.
HBr and peroxide. So this was actually a review of a chapter 9 reaction that we saw. And then last but not least, allylic bromination. What do we need? This is a special reagent. We can't use Br2. We said Br2 will do addition to the alkene, like we saw in chapter 9. NBS, exactly. NBS and UV light. And NBS stands for what? Does anybody remember?
N-bromosuccinimide.
Yep, N-bromosuccinimide. So it's a bit of alphabet soup. Most people just say NBS. And that's used anytime you want to react at an allylic position. And it's important to remember that an allylic position is 1 carbon away from your alkene. So really that bromine could be installed on the top or the bottom. In this case, it doesn't matter because it'll give you the same product. And then what do we have to watch out for with this reaction in particular? Resonance, right? With resonance, you can delocalize your radical intermediate, and you can actually have bromine get installed in different positions. So you do need to watch out for that resonance. All right, I think that's where we'll stop for lecture today. What I want you guys to do is to get started on the synthesis activity. So if you can, try to partner up with at least one other person and see how many of these you can get through. What I'll do is tomorrow at the start of class, I'll post the key and then you can check your work. And then I'll have a new activity for us tomorrow that's very similar to this.